There is something almost magical about watching a massive steel ship float effortlessly on water while a small pebble sinks instantly to the bottom. The answer lies in one of the most fundamental yet misunderstood principles in physics: buoyancy. Most people learned about it in school, heard the name Archimedes, and moved on. But what they were never told are the deeper layers, the professional secrets, and the cutting-edge technologies that are reshaping how we understand and apply this ancient principle today. Buoyancy is not simply about whether something floats or sinks. It is about the relationship between an object and the fluid it displaces. And mastering that relationship opens doors to engineering marvels, life-saving equipment, and futuristic technologies that most people have never even imagined. The core principle states that any object submerged in a fluid experiences an upward force equal to the weight of the fluid it displaces. This is Archimedes' principle, discovered over 2,000 years ago. Yet its applications are still being unlocked in the 21st century. The secret that professionals in naval engineering, aerospace, and deep-sea exploration understand is that buoyancy is not a passive force. It is a dynamic tool that can be controlled, manipulated, and engineered with extraordinary precision. One of the most powerful pro tips in buoyancy management is understanding the concept of the center of buoyancy versus the center of gravity. Most people know about gravity pulling objects down, but few understand that the center of buoyancy, the geometric center of the displaced fluid volume, must be carefully aligned with the center of gravity to maintain stability. When these 2 points are misaligned, even a floating object can capsize or become dangerously unstable. Professional naval architects spend enormous amounts of time calculating these 2 points with extreme precision. Another critical pro tip involves the use of variable ballast systems. Rather than designing a vessel or underwater device with a fixed buoyancy, experts engineer systems that can actively adjust the amount of water or air within internal chambers. Submarines are the most well-known example, but this technology is now being applied to underwater drones, research platforms, and even experimental aircraft that operate at the boundary between air and water. The ability to shift buoyancy dynamically allows for a level of control that static designs simply cannot achieve. A third professional insight involves the thermal properties of fluids. Water density changes with temperature, and this directly affects buoyancy. Cold water is denser than warm water, meaning an object will experience greater buoyancy in colder environments. Deep-sea researchers account for this by designing submersibles that can adjust their buoyancy as they descend through thermoclines, layers of water where temperature drops sharply. Ignoring this factor has led to catastrophic failures in underwater missions, while accounting for it has enabled record-breaking dives to the deepest points on Earth. Surface tension is another often overlooked factor. While it plays a minimal role in large objects, at the microscale, surface tension can dramatically influence buoyancy behavior. Engineers designing microfluidic devices and nanoscale systems must factor in surface tension as a competing or complementary force to buoyancy. This knowledge is now being applied in medical diagnostics, where tiny droplets and particles must be precisely controlled within fluid environments. The materials used to achieve and control buoyancy have undergone a dramatic transformation in recent decades. Traditional approaches relied on hollow chambers, wood, or foam to reduce overall density. But modern material science has introduced options that were once purely theoretical. Aerogel, one of the lightest solid materials ever created, has a density so low that it can float on air currents and provides extraordinary buoyancy when used in underwater applications. Its thermal insulation properties also make it ideal for deep-sea equipment, where temperature management is critical. Syntactic foam is another game-changing material that has become the backbone of deep-sea buoyancy engineering. Unlike conventional foam, syntactic foam is made from hollow glass or ceramic microspheres embedded in a resin matrix. This structure gives it an incredibly high strength-to-weight ratio, allowing it to withstand the crushing pressures found at depths of 6,000 meters or more. The submersibles that reached the Mariana Trench, the deepest point on Earth at nearly 11 kilometers, relied heavily on syntactic foam to maintain buoyancy under pressures that would collapse conventional materials instantly. Graphene-based composites are now entering the conversation as well. Graphene is 100 times stronger than steel, yet incredibly lightweight, and researchers are exploring how graphene-infused materials can create ultra-thin buoyancy structures that are both stronger and lighter than anything previously available. These materials could revolutionize the design of underwater vehicles, floating platforms, and even personal flotation devices, making them more effective while dramatically reducing their size and weight. Shape memory polymers represent yet another frontier. These materials can change their shape in response to temperature or electrical stimuli, allowing buoyancy devices to physically alter their volume, and therefore their displacement. Imagine a buoyancy aid that automatically expands when it detects cold water, the kind of water associated with dangerous conditions, and contracts in calm, warm environments. This is not science fiction. It is an active area of research with working prototypes already in development. Artificial intelligence and machine learning are now being integrated into buoyancy management systems in ways that are fundamentally changing what is possible. Modern autonomous underwater vehicles, commonly known as AUVs, use AI-driven buoyancy control systems that can make thousands of micro-adjustments per second. These systems analyze real-time data from pressure sensors, temperature gauges, and accelerometers to maintain perfect neutral buoyancy regardless of changing ocean conditions. This level of precision was simply impossible with manual or even basic automated systems. The result is underwater vehicles that can hover motionlessly at any depth, navigate complex underwater terrain, and conduct scientific surveys with a level of accuracy that was unimaginable just 10 years ago. Electromagnetic buoyancy is an emerging concept that takes the principle in an entirely new direction. Rather than relying on fluid displacement, electromagnetic systems use carefully calibrated magnetic fields to levitate objects within conductive fluids. While still largely experimental, this technology has shown promise in laboratory settings for controlling the position of objects in liquid environments with zero physical contact. Applications range from precision manufacturing in fluid environments to advanced medical procedures where surgical instruments must be guided through the body's fluid-filled cavities without mechanical contact. Underwater habitat technology is another area where buoyancy innovation is making headlines. Companies and research institutions are designing permanent underwater living and working structures that use advanced buoyancy management to remain stable at fixed depths without anchoring to the seabed. These habitats use a combination of syntactic foam, variable ballast systems, and AI-controlled thrusters to maintain their position in three-dimensional space. The implications for ocean research, resource extraction, and even tourism are enormous. Buoyancy-powered ocean gliders represent one of the most energy-efficient technologies ever developed for ocean exploration. These devices move through the ocean by cycling between positive and negative buoyancy, converting vertical motion into horizontal travel through the use of wings. They require no propellers and consume a fraction of the energy of conventional underwater vehicles. Some gliders have traveled thousands of kilometers on a single battery charge, collecting oceanographic data across entire ocean basins. The data they gather is transforming our understanding of ocean currents, climate patterns, and marine ecosystems. Looking ahead, the intersection of buoyancy science with quantum materials, biotechnology, and space exploration is opening possibilities that challenge the boundaries of imagination. Researchers at several leading universities are investigating bio-inspired buoyancy systems modeled after marine organisms that have evolved over millions of years to achieve perfect buoyancy control. The cuttlefish, for example, uses a porous internal shell called the cuttlebone to regulate its buoyancy with extraordinary precision by controlling the ratio of gas to liquid within its chambers. Engineers are now designing synthetic versions of this biological system using advanced ceramics and microfluidic channels, aiming to create buoyancy devices that are as efficient and responsive as nature's own solutions. In the realm of space exploration, buoyancy concepts are being adapted for use in the liquid oceans believed to exist beneath the icy surfaces of moons like Europa and Enceladus. NASA and other space agencies are developing submersible probes designed to operate in these alien oceans, where the fluid composition, temperature, and pressure conditions are radically different from anything on Earth. The buoyancy systems for these probes must be engineered to function in environments that have never been directly observed, requiring entirely new approaches to fluid dynamics and material science. Floating cities are no longer purely the domain of science fiction. Serious engineering proposals now exist for large-scale floating urban structures that use advanced buoyancy management to remain stable in open ocean environments. These structures would use distributed buoyancy systems, where hundreds of individually controlled buoyancy modules work together to maintain the stability of the entire platform, even in rough sea conditions. The technology required to make this a reality is being developed right now, drawing on everything from AI control systems to next-generation syntactic materials. The story of buoyancy is far from over. What began with a Greek mathematician in a bathtub has evolved into one of the most dynamic and consequential fields in modern engineering and science. The secrets held by professionals, the revolutionary materials emerging from laboratories, and the intelligent systems being developed today are collectively building toward a future where buoyancy is not just a physical phenomenon, but a precisely engineered capability that will shape how humanity explores, inhabits, and interacts with the fluid world around us.